Now that we understand the basic premise, let's dig a little deeper in our topic. So imagine that this is our RBC. Now RBC is missing two very important organelles, and those are nucleus and mitochondria. Okay? Now we're going to deal with mitochondria in this topic rather than the nucleus. Why? Because the major source of energy in RBC is really glycolysis. Why? Because there is no TCA, because there is no mitochondria. So the major source of energy for RBC is glycolysis. Okay? And the major pathway through which the RBC can protect itself from oxidative stress is the HMP shunt. Okay? Because the HMP shunt produces NADPH, and this protects, the whole pathway protects RBC from further damage. As a result, glycolysis and HMP shunt is particularly important in our RBC. So now going back to our previous diagram, one of the clinical correlation associated with this pathway is that if you don't have NADPH oxidase, you are going to have CGD, a chronic granulomatous disease, and I'll tell you why. When you have deficient NADPH oxidase, can you make oxygen radical? No. Can you make hydrogen peroxide? Not by the cell, no. Can you make HOCl? Not really. As a result, how are you going to kill this bacteria? What is your mechanism, right? So that's why when you have NADPH oxidase deficiency, you have chronic granulomatous disease, or you get chronic infections because you cannot kill those bacteria. So the test that we use for detecting if someone has CGD, or if we are suspecting if someone has CGD, is nitroblue tetrazolium test. Now, why is this test interesting? Because this test is going to measure our oxygen radical, okay? And if we do have NADPH oxidase, we will be making oxygen radical, and the test will turn blue, showing us positive. So if you're positive for nitroblue tetrazolium test, then that means you do not have CGD. Don't get confused. If the test is negative, then you do have CGD because you're not making those oxygen radicals. So moving on from that point, if you have CGD, you might not have NADPH oxidase, right? But what about superoxide dismutase? What about myeloperoxidase? Are they going to be present? Absolutely. Why? Because these are not deficient enzymes. So what is interesting is that even though the cell cannot make their own hydrogen peroxide because of missing NADPH oxidase, so this step is not going to go, this step is not going to go, so the cell will not be able to make hydrogen peroxide. So even though you have superoxide dismutase, it doesn't really help, because superoxide dismutase can only convert oxygen-free radicals to hydrogen peroxide. What interesting thing happens is bacteria, in fact all living organisms, are capable of generating hydrogen peroxide. So let's say you have this bacteria floating around here. It comes and makes hydrogen peroxide, because most living organisms can make hydrogen peroxide. The cell can use this hydrogen peroxide to make our bleach. How amazing is that? The bacteria is creating hydrogen peroxide, and the human body is using that hydrogen peroxide to make bleach, to kill the bacteria with a product that they made. So I thought that was kind of an interesting point. Now, even though the bacteria is making hydrogen peroxide, these hydrogen peroxide needs to be broken down, and we are using glutathione peroxidase for that pathway that we just talked about. Now, glutathione peroxidase, this step can also be achieved by an enzyme called catalase. Okay, catalase. And why is this important? This is important because if you have bacteria which can make catalase, for example, Staph aureus, okay, this can make catalase, and you use hydrogen peroxide to kill catalase in our body. I mean, to kill Staph aureus in our body. But Staph aureus can make catalase. As a result, what Staph aureus does is it can convert this hydrogen peroxide into water and oxygen, just like our body. Okay, so that's why Staph aureus is so dangerous, because Staph aureus has catalase which can convert the hydrogen peroxide created by our body to kill to kill the Staph aureus, but it uses that hydrogen peroxide to make water and oxygen using the same enzyme that we use, catalase, by converting hydrogen peroxide to water and oxygen. So now let's make it a little bit more interesting. So we saw that if we have a CGD, or if we have deficiency of NADPH oxidase, we can still kill bacteria by using the hydrogen peroxide that is being made by our bacteria. But instead of NADPH oxidase, what if you have deficient myeloperoxidase? What if that is the enzyme that is deficient? If that is enzyme deficient, then there is no way out, really, because then even if the bacteria is making hydrogen peroxidase, you can't kill it, because you cannot convert the hydrogen peroxide into bleach to kill your bacteria. So that is a much more dangerous situation than CGD. So now those were some of the pathologies associated. In the end, I would like to mention that in your cell, if you don't have, proper glycolysis, for example, your glycolysis is going on and there is no proper glycolysis happening, which is giving us pyruvate, then you are going to have chronic hemolytic anemia. And the reason you're going to have chronic hemolytic anemia is that because the cell is not generating any ATP at all. If your glycolysis is messed up, especially in our RBC, if you're not having proper glycolysis, then how will RBC survive? Because it has practically no energy, right? That is one common example of this, is deficiency of pyruvate kinase, the autosomal recessive problem. By the way, most enzymatic deficiencies are going to be autosomal recessive, 99.9%. In fact, I don't know any enzyme that is autosomal dominant problem. So pyruvate kinase is an autosomal recessive deficiency. So if you have autosomal recessive deficiencies such as pyruvate kinase, which will not allow your glycolysis to continue in a proper way, then you're going to have chronic hemolytic anemia, because the RBC are going to constantly lyse because there's almost no energy generated. But if you have problem with the HMP shunt, then the anemia is not going to be chronic. The anemia is going to be episodic. And the reason it's going to be episodic is because, they're not going to constantly break. They're going to break when the oxidative stress is really high, and the RBC cannot keep up with the oxidative stress because it cannot neutralize it using the HMP shunt. So that's why the hemolytic anemia with HMP shunt problem is going to be episodic, where a glycolysis problem is going to be chronic hemolytic anemia.